in this video, I'm going to be going through an ACE Physics Lab Practical Paper 3. This is the lab practical from the Summer Administration 2017, Paper 31. And it reads, in this experiment, you will investigate the motion of oscillating table tennis balls. Take each ball to a length of string, ensure the total length of the string and ball is 35 centimeters as shown. So one of the pieces of apparatus that we are provided is a meter rule. All right, so I've got a length of string here. It looks to be about 35 centimeters. And I'm trying to like tape one ball onto the end of the string. Okay. So each ball, so I got two strings. We want to be 35 centimeters. You see what it shows from the end of this to the end of the sphere. And so what I could maybe do is maybe adjust the tape. I'm taping it down so that it is that. All right. So you have an hour to, sort of wrestle your way through this. All right, so I wanted to do the end of that there. So all right, so you've got a 35 centimeter length of string with the ping pong ball sort of attached to that. It says set up the apparatus as shown in figure 2.2. So we've got two ring stands. Here, so these things up here are called bosses. And then you've got a horizontal sort of bar here with the two ping pong balls are suspended onto the bar, so it's secure to the other side. Sure. Angela. Now here's where I was kind of double checking to make sure like you should both be the same length, right? So if one is obviously longer than the other one, I would make that adjustment. I kind of say, well, okay, I try to do my best to kind of lay this down. So 35 centimeters from there. So this one I think is a bit long. And this one is also a bit long. Okay. Now here I could decide like, okay, well maybe what I want to do is put the ruler like this, kind of pull it back down, and then just make the adjustment itself like this right now. And, it really is, tough in a year like this where, we're sort of restricted to high contact surfaces and things like that. You really gain a lot of what's called tacit knowledge just by doing, experiments like this. Like it's hard for me to teach you in a book like, the ping pong balls aren't quite the length you want. You bunch up the string like this, read that and it's like you just kind of figure out doing lab work and oh, this is how I can make it work. And sometimes you go off to college and it's like you think like, well, this is like the right way to do this. And you find that like students that have had a lot of experience doing lab work, like in high school, will jump right in and so figure it out, make it work. And it's just like a great to touch this stuff, like, well, I don't want to break something, or you just like they've never done a lab before. So again, so that seems a bit better. And mindful of things that say like approximately, it's like here's the ensure the total length of the string ball is 35.0 centimeters. It doesn't say approximately. Sometimes it will say like, yeah, because you're going to measure it anyway. So it's like, put for example, the first one experience with the potentiometer might say, place the lead 50 centimeters down, or approximately 50 centimeters. Now say measure. So it's like, oh, it's actually 49.8, right? So I have set up the apparatus as shown. Pretty good. So set up the apparatus as shown. Check. Do exactly what it says. Okay. So the next step here says, pull one of the balls towards you through a short distance. Release the ball and determine the time for 5 complete oscillations. Okay. Something the right way. Good. All right. So now I will go ahead and do this one here. So I'm trying to determine the time for 5 complete oscillations. All right. So I'm going to go ahead and let you all do that. Start. 1, 2, 3, 4, 5. Okay. Now, if we were to say, okay, I got 5 oscillations, I wrote down the time, move on to the next step, you might lose a mark, okay, for this one. Anytime you're timing something, you should do what? Repeated trials, okay? So I'm going to do the same thing again. 1, 2, 3, 4, 5. That time was 5.82. And rule of 3 times. 1, 2, 3, 4, 5 oscillations. 5.96. Well, I know I said do exactly what it tells you. It doesn't say to repeat the readings, but it does say to determine. Okay, and the way to determine the time of 5 oscillations is to repeat the reading. Now it says, so what I would do to get this time is just average these, right? So we've got 6.02 plus 5.82 plus 5.96 divided by 3, so 5.93. Now it says, repeat the interval. One, 2, 3, 4, 5. Now that one was exactly 5.93. That would be the average of the other times, like you do. Keep that one. 1, 2, 3, 4, 5. 10.94. And a third time. 1, 2, 3, 4, 5. 5.89. Five point nine three plus 5.94 plus 5.9 3 5.92. Pretty good, right? We've explored the idea of pendulum earlier in the year, and remember that it's the length of the pendulum, which we kind of inferred was the same, and the gravity field that we're in, that's certainly the same, that determines the time period of oscillation. We would expect, if you kind of have that theoretical sort of understanding, these values to be nearly identical. So the same. It says remove the balls and strings from the wooden rod. Take the shorter wooden block to one of the balls, as shown in figure 2.3. Tape should be used on opposite sides of the block and the ball. Okay, so you're given sort of these two blocks as additional apparatus. Now we want to do this guy out. And every year, you know, I also enjoy the pleasure of doing these labs because you have to submit what is called supervised results. And so I come in early in the morning and do the same experiments that students do. So I enjoy all the same frustration venting on that last page there. All right, so we're trying to do something like that. Okay, something like that. Okay, just take the it says the distance between the end of the string loop and the mark around the wooden block is X. Okay, so it's like from the end of the string to this little midpoint, so like this line right here, that's X. We want to measure and record that value. All right, so you can, you know, sort of see just like I can. My judgment is, you know, so right away, it's kind of tough to judge, to sort of hold this next to the ruler because of the odd shape of the sphere. So that might be one of the things I kind of make a mental note of, like, well, maybe that's one of the things I'll say for a source of uncertainty. You know, it's difficult to take the measurement of X because it's sort of, you know, it's kind of faulty. So like, it's hard to like lay it over the top of that. So just kind of an odd thing to measure. Maybe that's a source of uncertainty. Then it's hard to say, well, what would I do to improve that? Is there a better instrument I could kind of use for that? So you want to have a corresponding suggestion for improvement with every sort of source of uncertainty at the state. So this is 36.6. Okay, I'm judging this to be 36.6 centimeters or 0.366 meters. So now you need to measure and record X, tell me exactly what that is, from that middle line to there. So I get 36.6 centimeters or 0.366 meters. Now they didn't restrict me in any certain unit, so it's just as acceptable to put 36.6 centimeters. Okay, I just kind of prefer to put everything in meters. Estimate the percentage uncertainty in your value of X. Okay, estimate the percentage uncertainty. Percentage uncertainty is calculated like this. It is the absolute uncertainty divided by the measured value. I know that the measured value is 0.366 meters because I just measured it. Okay, but what's the absolute uncertainty? And then, a percentage, so you have to times it by 100%. You'll get a ratio here that's a decimal that you convert into a percentage. The absolute uncertainty, there are different rules for how to calculate absolute uncertainty. For the time data that we just collected, for example, a moment ago, with this, one way, it's like, what's the absolute uncertainty? Right, there's some uncertainty in this. Okay, how much? One way to calculate it is to find a range of values. So the lowest value is 5.82, the highest value is 6.02, and half the range is one way to calculate absolute uncertainty. So the range would be 6.02 minus 5.82 for this data set. That's the range of values, 0.2. Half the range then would be 0.1. So the absolute uncertainty in these time data would be 0.1 second. Over the measured value, which would be 5.93, like the average of the measured value. Like which one of these, I measured all of them, which one do I use? I'll use their average. So that's one way to do it. That's one way to determine the absolute uncertainty, the way that I just showed, half the range. Half the range. Okay, half the range is one way to do it. Now we wouldn't use that technique for this set of data collection. Because if I have a range of values when I measure a length, it's only because I did a bad job measuring it the first time. Like if I measure something with a ruler, I should get the same measurement every time I measure it, unless I change something about it. Like, sometimes we'll like measure a piece of chalk and I'll write a sentence on the chalkboard and measure it again and say, oh, this is why the chalk is this much shorter, because all that chalk is still like conserved, right? Matter is conserved, so it's up on the chalkboard. But if I don't change anything about this, okay, the string black pendulum, and I measure it again, I should get exactly 36.6. In other words, you can't have an absolute uncertainty of 0. So if the range is 0, half of 0 is still 0, and we can't report that. So we need another rule for how do we determine the absolute uncertainty if the range of the measured values is 0. For time data, we usually get a different, like we will get a range like we saw, but for this, it's always going to be 36.6. Right? I'm going to hold the ruler up to it again. It's like, well, this time it's 40. Well, then you just didn't do a good job the first time measuring. Nothing changed about that. It should still be 36.6. Okay. And maybe I didn't do a good job measuring the first time. Let's take a look at that. actually like 37. So I'm just correcting that, but I took this measurement, but as I look at it a little bit more carefully, I tend to be 0.371, 37. All right. So the absolute uncertainty, the rule now, if you can't use half the range, is the smallest division in the scale. The smallest division in this scale is 1 millimeter, right? Like this is a meter rule and everything goes down to the single millimeter place. But I don't want to just say it's like 0.001 meters, right? So this is in meters, so try to be consistent. So 1 millimeter is 0.001 meters. But everywhere that I make a judgment, I'm introducing uncertainty. And so I can kind of think about like, I'm making a judgment about where does the end of my ruler line up with that edge of the loop, right? That's a judgment I'm making. So there's probably a millimeter of uncertainty there. I'm making a judgment about what line on my ruler matches up with like this line right here. And I'm also kind of eyeballing, you know, because I can't like lay it over top because the odd shape of the sphere there. So I have to kind of hold it next to it, like, you know, this kind of. And so there might actually be like 2 millimeters of uncertainty on this side, just because it's, you know, so he's kind of using your judgment here to say, okay, well, where is the actual, how much absolute uncertainty is there? And so I'm going to be kind of conservative here. I'm going to say that there is 0.003 or 4, I would say would be a good absolute uncertainty. You know, it's not to say, oh, this is a meter rule and it's accurate to the millimeter place, and therefore, you know, I'm just going to put 0.001. You want to really think about where are all of the uncertainties being sort of introduced there. If you take a look at the mark scheme for this, okay, the absolute uncertainty in X is in a range of 2 to 5 millimeters. Okay, the range, the one that we got earlier, 35 to 40, right? We said 37.1, so we're good. Did we get a time of 3 to 7 seconds earlier? We did. We were like right around 6, okay? And within 0.4 seconds of each other. And they were, right? They were actually very close together, right? So far we're doing good as we sort of go through the mark scheme and as we're sort of doing aloud, like, am I doing something completely wrong here? So, you know, obviously we shift to the paper with the benefit of mark. So if I were to estimate the percentage uncertainty now, remember it's the absolute uncertainty, and I'm good with this, right? So anywhere between 2 and 5, I said 3, so I'm kind of right in that. 0.003 divided by 0.371 was my measured value, and then times 100 out of percent. So I am getting the percentage uncertainty to be 0.003 divided by 0.371 times 100, and I get a percentage uncertainty of 0.8. 0.81% uncertainty in X. That's really low. Remember, ultimately what I'm going to do is I'm going to say, hey, if my percent difference in K is less than this, then the readings agree with the relationship. That's a pretty high threshold. Okay, in other words, that's less than 1%. I'm very certain in that measurement. Okay, I'm within 1%. It might be, you know, 1% off. Set up the apparatus as shown. Okay. Pull both balls towards you. Release the balls at the same time and watch the movement. The 2 balls will move backwards and forwards, becoming out of phase. After a time, they will be back in phase so that they move towards you together. The ball with the block attached completes N oscillations in this time. Okay, so sorry. With me. So here's my next instruction. Pull both balls towards you, release them at the same time off the movement. They will move backwards and forwards and become out of phase. After a time, they'll be back in phase. So if you move towards you together. The ball with the block attached contains n oscillations in this time. Okay. Repeat and record now. Sort of like, hey, just do that one time. See it. Now, okay, do it again now. And this time, actually, count n. All right, and record that. Okay, so right away, okay, this is a problem. See? The way that it's taped isn't very secure. And so if I'm like bunching up the tape in order to get that original length, but then it's sort of coming loose, right? And I'm sort of losing that original value. So I would definitely list this. Remember, I kind of previewed the lab and had that page where it's like, what's the source of uncertainty? I would list, attaching the string to the ping pong ball with the tape, is not a secure means of attaching it and become undone and obviously affect the result if we're sort of relying on the consistency of the length of it. And so this one hasn't changed, right? That's my 35 centimeters. And so the bottom of this, should be sort of on par with that, but then did I just change my measured value? And this is where you have to kind of decide, should I repeat that reading? Should I take that measurement again because maybe I measured something that's kind of off here. And it really is up to you to kind of decide that. Very high sensitivity. All right, I already kind of see a problem. This thing crashes into this, right? That could be another thing. If brass is too close, it affects the oscillations. So you want to kind of be mindful that you've got some thoughts in mind to answer that sort of final part. All right, so here's what we want to kind of observe now. Pull towards me and release. And see how they go out of phase. Okay, so like one is going towards, the other is going away. But eventually, they'll come back in phase right there. Okay? So again, our phones, they're in phase right now, right? They have the same displacement. And as I release them, they quickly go out of phase, right? So one's towards while the other's away, to and fro. And I've been counting, I've been spying, this one because I want to count how many oscillations end until they're back to there. Okay, or they're moving together. All right, so that's sort of my goal. All right, we'll do that. Remember, we're counting n oscillations for the moving block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I think. The 14th one, right? And equals 14. Now, should we repeat that? I think it's probably worthwhile to repeat that. So let's see if we also get 14 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe the 15th time on that one. Trial 2, 15. Okay. 1, 2, 3, 4, 9, 10, 11, 12, 13, 14. Well, probably 14. Okay, 14, 15. Now it says to calculate n plus 1 over n squared, or n plus 1 squared over n squared. So this would be 15 squared over 14 squared. 15 squared over 14 squared. 1.15. Use the longer wooden block and repeat, starting from C1. So that was going all the way back to here. Okay. Measure X for that one. Everything that we just did with the shorter wooden block, we do with the longer wooden block. So here we've got 40.8. 0.408. All right. 1, 2, 3, 4, 5, 6, 7. One, 2, 3, 4, 5, 6, 7. Okay, feel good about that. So now I want to remember 7 plus 1 is 8, 8 squared is 64 over 7 squared is 64 over 49 for this quantity, which is 1.31. It now reads, it is suggested that the relationship between n and x is this. where k is a constant. Using your data, calculate two values of k. Well, I've already calculated this. So for the first one, I've got 1.15 equals k, and my x value for that one was the 0.371. So that would give me k1, okay, first value. The other one I calculated this term to be 1.31 equals k, and that's where x was 0.408. And so the calculation of k is worth a mark. That's not too bad. I'm just dividing divided x, so 1.15 divided by 0.371 gives me a value for k here 3.099. So I'm going to say 3.10 and 3.099. The second value of k would be 1.31 divided, that's not a negative, so I'm going to put the parent mark, divided by 0.408. And this gives me 1.15 divided by 1.31. So this one gives me a value 3.21. Right. Now, to explain whether these results support the suggested relationship, I need to calculate the percent difference in k. The percent difference in k is going to be the difference in the values, 3.21 minus 3.1 over 3.1. Okay, over the original value or the lower value. 3.21 minus 3.1 divided by 3.1 times 100. So the percent difference in k, percent difference in k equals 3.6%. So that's how far off these values are from each other. Is that close enough that I could say that these values support this suggested relationship? I need to compare it to my percent uncertainty and my other values. So because earlier I've already determined the percent uncertainty and my value of x to be 0.81%, well, that's bigger than it. So these readings are not consistent with that relationship, and that's okay. So as long as you correctly apply that criteria, it's not that the readings will always support the relationship. So I would say something like, because the percent difference in k is greater than the percent uncertainty in x, the readings or the results do not support the suggested relationship. A few years ago, students were joking that this would be a good physics way to look at your. I'm sorry, but these readings are not supporting the suggested relationship. So I became that percent difference. Well, the effective length of the pendulum formed by the ball of the string is L. Use your second value of k to calculate L using the relationship k equals 1 over L and give your answer to 3 significant digits. So that mark there is just kind of like, okay, my second value of k is 3.21 equals 1 over L. So I multiply both sides by L, so through this, 1 divided by 3.21, and I get 0.3. 0.31, okay, which is pretty close, right? Because we measured that, right? The length of the string about 35. Now, for 3 significant digits are 0.312. All right, and then the last bit of this that I'm not going to sort of go through now is, remember, 4 sources of uncertainty and then 4 suggestions for improvement. The first one can always be 2 values of x, and n plus 1 squared over n squared is not enough. So you could take more readings and plot a graph, right, like we do with the first experiment. So that's always kind of the first one that you could, bank, and the other ones might be, the tape is difficult to secure, find a better way to secure it, by attaching it with putty or something like that. It's a little bit more, sturdy than just like a piece of tape that can kind of unravel. So you kind of, could sort of think your way through that. And, we'd also take a look at the mark scheme here. And let me show you what they said for this one, okay? So they said 2 readings are not enough to draw a valid conclusion, but they would not accept not enough for accurate results or few readings. You say 2 readings are not enough to draw a valid conclusion. So take more readings and plot a graph. Take more readings and compare k-values. Not repeat readings on our own. Okay, so see how that's always the first one. Difficult to judge when the balls are back in phase, and so video film are recorded. Okay, see from the side. Balls hit each other, they're blown by moving air, move sideways, regular movement. You might notice that, especially the second one, right? Like, is that really accurate? Kind of moving irregularly. So again, they're sort of expecting there's problems with the lab, and they want you to find it too. I noticed this, damping, the oscillations die out quickly. Because it's ping pong balls, they're very light, right? And so the air affects their movement a lot. So they say, turn off the air conditioning, use a windshield, okay? Improve the method of measuring this using clamps to fix the looping ball, okay? Remember, so it's kind of tough to measure that. So use a clamp, hold it down. Improve method for attaching, glue, Velcro, stick to your tape, stronger adhesive, right? And so again, they're sort of recognizing or anticipating those problems and are hoping to do these too. So only 4 of these, the maximum of up to 4. There's a lot of things you could say, right? And so you want to kind of be mindful that 8 out of the 20 marks on the second experiment come from this page right here. And all the rest are just kind of practicing with those calculations. This is then the paper 3 with Dr. Flood. We'll see you next time.